Hi everybody. Today I thought we'd have a look at designing and building a 6.5 digit voltmeter. I've labelled this project a millivolt meter essentially because it's capable of measuring down into the millivolt range or better. But following a number of requests, I will make sure that this project can handle input voltage all the way up to around 50 volts. So it gives you a nice wide span. The intention is to make this affordable for the hobbyists. The total cost of this project will be between £30 and £40. And when you consider that if you had to buy a 6.5 digit voltmeter or multimeter, they're quite expensive for the hobbyist to afford. So hopefully this little project will give you something that is useful and comparable with some of the more expensive meters you see on the market. So I think the first thing we'll do, we'll have a look at the block diagram of the project I proposed today. Right, well, here we see the basic block diagram of the project I proposed today, and the heart of it is going to be a 24-bit analog to digital converter IC, and the one I propose using today is the Linear Technology LTC 2400 chip, which is ideally suited for our project today. It's a very accurate 24-bit ADC. It has very low noise. It operates off a single supply voltage, so in our case we're going to operate it off a single 5-volt supply. It's very low current, only takes around 200 microamps, and the total error over the full range of the conversion is only about 4 parts per million. So it's ideally suited for our project today. Now the input to this ADC, I'm going to use a little buffer there, probably an operational amplifier wired as a unity gain device, just to give some isolation between the input of the ADC and the network divider that I'm using on the input. And I've decided to use a divide by 10 resistor network on the input, and the main reason behind that is that I wanted to be able to widen the range of the voltage reading of this millivolt meter. And by using a divide by 10 at the input, it means I can have a possible range up to around 50 volts, 0 to 50 volts. The reason there being is that the input to the analog digital converter IC, it can only handle around 5 volts on its input. So dividing it down by 10, we can take it down by that factor, and then we can use the Arduino here. We're using the Arduino Nano to take the binary data out from the ADC and convert that to be displayed, and we can also then within the program allow for the divide by 10 that we had here on the input. Now the accuracy of the 24-bit ADC is dependent on a precise voltage reference source, and for that we're going to use a 4.096 volt precision reference source here, and I'll go over that shortly in terms of the chip I've decided to use for that. But for the moment it's a fixed very accurate reference source supplied to the ADC, and that is then divided down into the 24 bits to give us the accuracy of the meter itself. Now the output from the 24-bit ADC is fed into the Arduino Nano here, which I'll program to convert the binary signal into a decimal signal to be displayed on a LCD display. And the one I'm going to use today is a small 16 by 2 LCD display, and we'll display probably down to 5 or 6 decimal places. Now the other point I will make is, because we'll have a few built-in errors here and probably a little bit of noise in the circuit, I wanted some means of calibration. So I'm going to include a little calibration button on one of the input pins on the Arduino, which I can then program to calibrate the meter when we first switch it on. Now the whole circuit itself here is going to be driven by a 5-volt supply. I'm just simply going to use a little 5-volt regulator, the 7805, and then feed that from probably either a 9-volt battery or a number of AA batteries to that level. So there we have it. There's the basic block diagram. And what I'll do next, I'll just explain the particular IC that I've chosen here for the voltage reference, because I had a number of requests on some of my previous videos asking what was the decision process in deciding which particular IC or component I was going to use. So I'll just, as an example, I'll just show you my thought process in choosing the voltage reference here for this particular project. And I've just shown here three different ICs, although there was many more that I looked at. But just to give you an indication of what I'm looking for when choosing an IC for this project, I've put three down here which we can compare, and we can look at the data from the data sheet to compare each one. So the three I'm going to look at here is the Analog Devices ADR4540, and this is going to be the B grade of that particular IC. You'll find in all these voltage reference ICs there's different grades within the same IC. Obviously the better the grade, the more costly the IC is. But I'm comparing like for like in this particular analysis here. I'm also going to look at the Texas Instrument, the REF3240. And finally, I'm looking at a Maxim, the Max 6341. That's the C grade version of that. Again, I'm trying to keep them comparable in terms of the specification for those three ICs. Now, the first thing I'm looking at here is the input voltage range for these ICs. And remember, our project today, we're operating everything off a 5 volt, a regulated 5 volt supply. So ideally, we'd like to have a IC that operates at 5 volts. And you can see straight away here that the bottom one here, the Maxim, normally operates between 8 and 36 volts. So, you know, really it's not particularly suited to our project today. But even so, there is ways around that. Since we're using a 9 volt battery before it goes into the regulator, there is ways of actually getting around that. But it would make it easy if we stuck at 5 volts. The next thing I'm looking at here is the initial output error. Now, most people think that when you're choosing a voltage reference IC, you choose it for the best accuracy. If you have a reference IC that says it's an accuracy of plus or minus 0.01%, that is much better than going for one that is plus or minus 0.02%. But accuracy is not always the important factor when looking at things like a digital voltmeter. And the reason behind that is it's the long-term stability of that meter over time that is important. And the other point to remember is that any inaccuracies in the initial voltage reference, we can actually cancel that out by calibration, by putting some offset voltage to calibrate that. Now, looking at the initial input errors here, you can see that the Analog Devices IC here has got a maximum error of plus or minus 0.02%, which is quite good. Whereas the Texas Instrument IC here, they're quoting on their datasheet typical error of plus or minus 0.01%, which is even better. However, when you read into that datasheet, it does also then say that the maximum error can be anything up to 0.2%, which is not so good. So, you know, you've got to look at the specification in the round, really. And then the bottom one here, the Maxim, is similar to the Analog Devices one. That's got plus or minus 0.02% error. So all three ICs are quite good. Initially, you would think the Texas Instrument is the best of the three in terms of initial accuracy. Now, the next factor I'm looking at here is the temperature coefficient of the IC. That is the drift in parts per million as the temperature increases. Now, obviously, we want to keep that as low as possible. And you see here that the Analog Devices one has got 2 parts per million per degree centigrade, whereas the Texas one is much higher at 7, so that's not so good. Whereas the Maxim is even better at 1, so the maximum is better in terms of temperature coefficient. Now, the next factor I'm looking at on the datasheet is the line regulation, and that's in parts per million per volt. And the lower that figure, the better, really. And you can see straight away that the Analog Devices one has only got a 1 parts per million per volt line regulation. That's the stability on the regulated line. Whereas the Texas Instrument one there is 15, and the Maxim one is 10. They also quote on the data sheet the maximum line regulation drift there, which you can see is 10, 65 and 30. So the figures I've got initially are the typical figures of 1, 15 and 10. The next point you need to look at on the data sheet is the output noise. With a digital voltmeter, the last thing you want to do is have lots of noise, because lots of noise can affect the reading and the stability of the reading. So you want the noise to be as low as possible. So you see here that the analog devices one has got a noise of 2.7 microvolts peak to peak, and we've got 53, which is much greater there on the text instruments, 53 microvolts peak to peak, and then the maximum one is even better, 2.4 microvolts peak to peak. So in that relationship, the maximum IC seems to be the best in terms of noise. Now the next thing I look at on the data sheet is something called the thermal hysteresis in parts per million. This is the stress, the thermal stress on the IC, and again you want to have that as low as possible. You'll see that the analog devices is 50, however in this case now the text instrument one is much higher at 100, so that's not so good, and the maximum is even better at 20. And then the next factor I'm looking at here is the turn on time, or the settling time. And again, if you wanted to respond very quickly at switch on, you wanted to settle down quickly, that could be important, and that's given in microseconds. And you'll see that the analog devices chip there is 155 microseconds, whereas the text is 60 and the maximum is even better at 8. And finally, we're looking here at the long-term drift over, normally they quote on the data sheet over a period of 1,000 hours, and that's in parts per million, and again the lowest on that is the best. So you can see here that the analog devices I see at 25 parts per million is much better than the Texas at 55 or the Maxin at 30. Now for our particular project today, the important things really are going to be the output noise, the temperature coefficient, the line regulation, and the hysteresis, thermal hysteresis, and the long-term drift. And I've sort of said that those areas are the most important in terms of what I'm looking for today. And looking at the overall data of these three ICs, I decided at the end of the day to go with the analog devices IC, the ADR4540. And the main reason was it operates off 5 volts quite nicely. It has a very good, in any way, initial accuracy of 0.02% error. And the temperature coefficient, the line regulation is excellent. The noise is very, very low. It's certainly comparable with the Maxim IC. The thermal hysteresis is still quite good at 50, and the long-term drift is the best of the three ICs. So the long-term drift is quite important for our voltmeter today. So there we are. That's what I've chosen today, the analog devices IC, and that's what we'll use in our circuit. So I just thought I'd go through that process, and you can look at how we can compare the specification with different ICs and how it suits your project. Well, let's have a look at the full schematic for this project today. The input to this circuit is coming from a divide by 10 resistor network here. I haven't quite decided yet exactly what resistor network I'm going to use. We'll have a look at that when we come to building the project. But in any case, I want to try and keep the resistors as high as possible to avoid any loading on certainly small voltage sources, and we need to have the divide by 10 ratio there. So we have that network on the input. I then have a 5.1 volt Zener, and that's just for protection really, to prevent the input voltage going to the operational amplifier from exceeding around 5 volts. The operational amplifier there, the OP777, I'm using that simply as a unity gain buffer. It'll have a high impedance input, so it's acting as a nice buffer between the divider circuit here and the ADC there. So the output from the buffer at pin 6 is then fed to pin 3 of the analog digital converter IC, and I decided to put a small 1 microfarad tantalum capacitor there and a 10k resistor to give some sort of noise rejection on the input of pin 3 on the ADC chip. The reference voltage to that IC is coming in on pin 2, so that's our 4.096 volts reference, and that's coming from the ADR 4540B chip, the analog devices IC, from pin 6 there. Now, the important thing of these ICs is it does need a capacitor on the output for the voltage reference IC to work correctly. They say in the datasheet that any capacitor from 0.1 to 10 microfarad is suitable, but obviously the larger value you put there, it will slow down the settling time of the reference voltage, so the trick is to keep it as low as possible. So I've decided to use a 0.1 microfarad there on the output. Now the input supply to this is coming on pin 2, the 5 volts going on pin 2, ground is pin 4, and again you need to add some filtering on that as close as possible to the IC, so I've added a 3.3 tantalum and a 0.1 capacitor ceramic on the supply voltage input to that IC. Now again, looking at the analog digital converter IC, the outputs from this IC, the data and the clock, you'll see here that we have the data coming out of pin 6 and going to D12 of the Arduino, and the clock signal is coming out of pin 7 and going into pin 13 of the Arduino. The pin 5 of the ADC is actually the chip select pin, and we need to take that low to make the converter active. When it's high, it's in held off state. We take it low to make it operate. So I have a voltage coming out of pin 10 of the Arduino there that simply takes pin 5 low when we want the ADC to start working. And then when we want it to stop, we just take it back high again. I've also decided to add a couple of pull-up resistors there, two 10k resistors on both the data line and the clock line, those two resistors there. Now on this particular IC, on pin 8, you have an option to use one of the built-in notch filters inside the IC. There's a notch filter operating at 50 Hz and one at 60 Hz, and you can simply select which one you want to use by either taking pin 8 high for 50 Hz notch filter or low for the 60 Hz notch filter. So what I'm going to do is just put a little few pins there that I can then just plug a link in if I find I need to use that option. And then another important point is that on pin 1, which is the 5 volt supply to this IC, we need a little bit of decoupling there, so I've put a 10 microfarad tantalum and a 0.1 ceramic to decouple the supply voltage input on pin 1 of that ADC. Now the Arduino is not only taking the data from the ADC and processing that, it's then converting that into a digital number to feed out to a LCD display, and I'm using a 2-line by 16 LCD display there with a backlight. You'll see I've got a 220 ohm resistor there on pin 15 and 16 is grounded, and that is the LED backlight on that. The rest of the pins, pins 11 to 14, the data pins going in, and then they're going to the Arduino on these data pins here, and then the other pins from pin 1 are the supply and the enable and read write pins, etc. on the liquid crystal display. So that's what they are there. Pin 1 starts there, goes all the way down to pin 16. We have a little 10k preset there, which is simply setting on pin 3 of the display the contrast level for the LCD display itself. So there we have the basic circuit, and I think what we'll do now is we'll look at building that circuit. Obviously, because we're looking at a precise voltage reference here and everything else, it's not ideal to build that on a breadboard, although you could try it on a breadboard. But I'll look at building that on a printed circuit board, and let's have a look at a PCB I'll design and the components we'll use, and then we'll build it and then we'll test it and look at some of the issues when we're testing the board and any changes that we decide to make. So let's do that next. Here we can see now all the components I propose to use for this little project today. As you can see, I've made a printed circuit board now for the project. I thought that would be better than trying to hook everything up on a breadboard. It keeps the noise levels low as well. And here we can see the component layout for the PCB. I'll make these available for you to download. Quickly go through the components. Here we have the liquid crystal display, 16 by 2 liquid crystal display. I'm using a white on blue background with a backlight, and I have a socket here which I'll solder onto the board so we can plug and unplug the LED module. So for that reason I've already soldered onto the LED module some header pins here, and then it'll just plug straight in onto the socket on the board. There's the multi-turn little preset we use to set the contrast for the LED. There's the 5.1 ceramic capacitors. There you can see I have a precision CADC potential divider network. The trouble with these is that they're quite expensive. This particular one I think I paid just over £10 for, but the tolerances are quite good, and I might just try that as the divider network on the input circuit for this project, but I'll also look at some other options using standard resistors, which are a lot cheaper to do, and maybe even have some trim control on there as well. But for the purpose of this, I've actually made provision on the printed circuit board so it could take this thick film resistor, but there'll be options on the board to solder on normal resistors, so you can take your choice on that. There you can see a little 3-pin connector link there, jumper link, with a little connector plug there, link at the top. I'll use that to select if I want to use the 50 or 60 Hz notch filters on the ADC. There we have the 3 ICs. They're all surface mount ICs that we mounted on the print side of the board, and here we have the Arduino Nano, which I propose to use, and I've decided to use some little standoff pins, so I'll put some standoff pins soldered onto the printed circuit board, and then they'll solder onto the Arduino Nano, and I think that'll make quite a neater job. So I'll just cut these down to size, and that'll help us to solder the Nano onto the board. Here we have all the tantalum capacitors we're using on the project, 10 microfarads and 3.3 and 1 microfarad. Here we have the 10k resistors and a 5.1 volt Zener. In addition to these 10k resistors, we also will have a 220 ohm resistor as well, which is not here at the moment. Battery connector for the 9 volt battery, a 220 microfarad electrolytic for the input smoothing. There's the 5 volt regulator. As you can see here, I'm using a TO2205 version of that, which is probably overrated really. You could actually get away with the 100 milliamp version on this project as well, so again that's up to your own choice. There's a little tactile button with its knob, which I'll use to trigger the calibration adjustment. So that's the components we propose to use. Everything's there apart from I've got a 220 ohm resistor as well, which will be the resistor feeding the backlight on the LED display. Right, I think the next thing we'll do is we'll solder the components on the board, and then we'll come back and have a look at that. Right, well, here we can see the printed circuit board now with all the components mounted. I haven't for the moment put the resistor network in on the board. I just want to look at the possible options for that, whether we use that or we use some standard resistors, which will be cheaper. But all the other components have been mounted there. The Arduino Nano, you can see, is mounted on the board using those little standoff pins. There's the little tactile push button for the calibration button, and there's the main smoothing input capacitor, and all the other components you can clearly see there. As you can see, I have the socket now mounted for the LCD display, and there's the little multi-turn preset for the contrast control for the display. So basically the display will simply plug in now to the main board. As you can see, I've also put some plastic standoffs here to support the LCD display as well. If we just have a look at the reverse side of the board, you'll see how I've mounted the ICs. Here we see now the print side of the board, and you can clearly see the three ICs there mounted onto the printed circuit side. They're all labelled U1, U3, U4, and I've labelled the voltage reference there. I have a test pin on the board I put on for testing the 4.096 volt reference. What we'll do, we'll just zoom into that and have a closer look at that part of the board. There we now have a clearer view of the three ICs. That's the voltage reference IC there. There's the analog to digital converter chip. That IC there is the buffer, the operational amplifier. Now I've marked on the PCB, there's a little round dot which indicates where pin 1 is for each chip. So you'll see a little dot there, and on the other chips I've done exactly the same. So make sure that when you solder them in, you get them in the correct orientation, and pin 1 lines up with the dot on the printed circuit board. Well, here we can see now a closer view of the component side of the board, excluding the LCD. There you can see clearly the Arduino Nano mounted onto the printed circuit board now on those little standoff pins. There's the tactile calibration button. Clearly see all the other components on the board. There's a little reference test pin there, where we can test the reference voltage, the 4.096 volts. We have a little pin there. There's the jumper pins to set the notch filter on the ADC, either 50 Hz or 60 Hz, or leave it out altogether. And you'll also notice I've put another pin there. It looks like a test pin, but it's an option for a future upgrade. I had a spare data pin, D9 I think it was, on the Arduino, and I've simply put that out to a little pin there, which we can solder onto for a later upgrade if we need to modify or upgrade this particular unit. I've also added a few links on the board. You can see that there's a jumper link there. There's also another jumper link under the LCD display. I'll show you that in a moment. And normally there would be a jumper link here. I've just soldered two wires in for the moment because I want to test this unit with normal resistors to see how accurate it is. But you can clearly see there I've got holes there which are designed to take the precision thick film resistor network, if that's what you decide to do. But these are quite expensive, so for the moment I'm going to leave that out, and I'm going to try a normal resistor network which is much cheaper and just see how the performance is. There's a view of the PCB under the LCD display. There you can see the socket, and that's the little shorting link I said. It's just a link in two parts of the printed circuit. It was easier to do that than rather than use double-sided print. So that's just a little link there. And the resistor there you can see is the 220 ohm, which is the feed for the backlight display on the LCD. And there you have the two standoffs. Right, well here, just in order that we can test the unit, I've made up a resistor network here. I've used two 1.8 megohm resistors in parallel, which will then give me 900k, and then I have 100k going down to earth, so it's 100k to 900k, so we're getting our divide by 10 network there with that arrangement. Now these resistors are just 1% tolerance at the moment. In fact, I think the 1.8 meg are 5% tolerance, so they're not the best, but at least it'll give us an indication whether this method will work. And if it proves satisfactory, then I'll use higher tolerance resistors here, and we'll can test it again before we finalise the project. So for the moment we have a divide by 10 resistor network here. Now what I've also done is I've uploaded into the Arduino some software that I've written for this project. I'm still working on that software. There's a few more enhancements which I want to make yet, and I'll cover fully the software and final testing and monitoring of the waveforms in part 2 of this project. But for the moment, so we can test the unit, I have installed some of the software into the Arduino, and I'll connect the battery and then we'll see what happens. There we have a get started with the display at the startup. Once the startup display goes after a few seconds, then you get on the display millivolt meter, and below that you've got the voltage reading. At the moment I've got nothing going in here, but the meter is giving a sort of a noise reading of 10.3 something of a millivolt. You can see there that we've got millivolt indication on the display. What I'm doing with the software for this is that if the voltage is below 1 volt, I'm putting the millivolt readings there. If it's above 1 volt, I'm putting the voltage readings. So that's all done within the software. So I think the first thing I'll do is just test whether the calibration feature that I'm working on is working. And to do that, what we need to do first of all is simply just short the input terminals together. So I'm just going to put a little shorting link between the input terminals there. And then having done that, I'll then just press the red calibration button. It says calibration, short input leads. It then calculates an adjustment factor which it shows you there, and then it'll revert back to the normal reading. So that is now calibrated. We may have to trim the calibration later when we finalise the project, but let's just see how it goes for the moment. So if I now remove the shorting link on the input, now obviously with any meter of this accuracy, it's picking up a little bit of noise on the input there, and it's showing it as a millivolt reading, 4.7 millivolts, and that's going down to 6 decimal places. But what I'm going to do, just to see how good this particular project is, if you remember on one of my earlier projects I built a little precision voltage standard, a little 5 volt precision voltage standard, which was accurate to plus or minus 0.01%. And I'm going to use this to feed this onto the input and see what that 5 volt reads on this little millivolt meter. So we connect the reference voltage, and then I'll just press the button to switch on the reference voltage, and let's have a look and monitor the display. And as you can see there, the display is reading 4.99697 of a volt. These reference voltage just take a little while just to warm up, and when it's warm in sort of a minute or so, we should get a 5 volt reading coming out. But even so, at the moment you can see there that clearly now we've got quite a good reading coming out here of 4.9977 or 6, and the last few digits are just fluctuating. So I think I'm quite happy with that. The unit seems to be working quite well. There again you can see I've got the V, so it's indicating that's a voltage reading. What I'll do, just for the hell of it, I'll just connect a millivolt reading to it and see what that reads. So I'll just connect a 50 millivolt reading to the unit. I've connected 50 millivolts now to this unit, and there you can see that we have a reading on the display here of 49.64 or something. It's fluctuating there, and there you can see now we have the millivolt reading on the scale. So So this seems to be working quite well. I need to do obviously some adjustments on the software to finalise this project, but at least we know the unit does work and we're able to drive the analog to digital converter correctly and read it on the display. Well, the project seems to be working quite well so far. The meter is displaying correctly, although we may need some trim on the final voltage reference coming out. We need to finalise the software in the Arduino here, which I'll do in part 2, and I'll go through the details of that software in part 2 together with the full testing. We'll check the unit on the oscilloscope and finalise the project. So we'll cover that all in part 2. In the meantime, I'll put the schematic and the PCB layout details in a link below, which you can download if you fancy having a go at this project. And I'll see you all again in part 2 for this project, where we'll finalise it and cover off the software. Thanks for watching. If this was of interest to you, please give me a thumbs up, and I'll see you all again next time. Bye for now.